Okay, so three talks by students from Turing class, Peking University, will be given in this CDM session. And the first talk is from Ding and Lin Xiaozheng. Ding and Lin Xiaozheng are junior undergraduate students of Peking University. Ding's research interests focus on network measurement and stochastic system with heavy traffic regime. Lin Xiaozheng's research interest is visual information processing and neuromorphic computing. The title of their talk is Mathematical Foundations of CTM. So now let's welcome.
Okay, then good morning. Today we're going to introduce some mathematical foundations of conscious Turing machine. I'm Ding, and here is my partner Lin Xiaozheng. We're currently at Peking University. So today's our discussion will be divided into these three parts, namely the notion of permutation invariance, and then we'll delve into the additive functions. The last part concerning the implementation of sleeping expert algorithm on this CTM model. And here we have some preliminaries to share. As we all know that a chunk can be in general expressed as this six-tuple, the address of the processor that originated this chunk, the time t at which it was generated. The gist and the weight field is the most important part of the chunk, that is how important this chunk is and what this chunk is about. And the intensity and the mood are the two fields remaining concerned here. And as we can see, the domain of all Lego chunks is exactly this set, where X is representative of this intensity field, and Y is exactly the mood field. And from here on, we'll use this symbol neo to denote the chunk whose intensity and mood are both zero. We're going to see that neo plays an important part here. So here we're going to introduce some notion. The first one is that since CTM is quite an artificial model, so the alignment of the processor on the leaf node quite matters. If in general, this alignment will affect the probability at which a chunk gets to the final STM. So we want a specific family of computation function in order to let this CTM to be permutation invariance. That is, the permutation of its leaves, that is the LTM processor, does not affect the probability at which each node is to be in STM after computation. And we call the computation function associated with a permutation invariant tree to be permutation invariant as well. So in general, we want to ask what permutation function will make this tree to be permutation invariance, and our answer is that the additive function will suffice. So the additivity. Here's the notion of additivity. A computation function f is additive if the f of chunk is exactly the sum of f of chunk at its two children. And here is a specific case for computation function. You can choose f to be independent of the specific value of the intensity and the mood, but indeed it is constant. It maps all chunks to be the same value c. So we are going to show that if a function is additive, then the CTM is permutation invariant and vice versa. Before we delve into the proof, let us build up some intuition first. What can an additive function look like? So the first example is here. We define f merely on the field of intensity. It is indeed an additive function. You can check this equation, yeah. And the second, we plus half of the mood here, and you can also verify that it is indeed an additive function. The third example is a nonlinear one. As you can see here, we multiply intensity with the mood, and of course, it violates its equation. The last example is a bit tricky. You can see here, it is defined merely on mood. It indeed satisfies this linear equation, but it is not additive function since the mood can be negative. So here we have two constraints. The first is this linear equation, and the second one is that f should map a chunk to a non-negative number. So first, we're going to show the sufficiency side. That is, given f is additive, the tree is then permutation invariant. Actually, we can compute the probability at which the chunk produced by the case processor eventually reaches this STM. It is exactly this fraction, that is the f of chunk k normalized by the sum of all chunks. We're going to omit the proof here since it's quite simple. What is interesting is actually the necessity side. That is, given a tree is permutation invariant, then its computation function must be additive. The general idea is here. We will repetitively exploit the property on the simplest tree that reveals this property, that is a binary tree of depth 2. As you can see here, an easy observation is that for a permutation invariant tree, each of its subtree, that is the triangles depicted here, is also permutation invariant. So in the proof, we will generally view it as a single node hooked on this leaf. It has the advantage that now the chunk produced by the processor can not only be the initial chunk, but any chunk that is legal. So first, we were going to show, so the key problem is that what can f of neo be? This is the first step of our proof, actually. If it's positive, that is, we denote it as C, let us consider this scenario. You can see that we hooked 3 identical neo chunk on the list, and the last one is an arbitrary chunk. So we are going to compute the probability at which these 2 chunks will win. Since they are identical, we naturally would expect that the probability be the same as well. So the probability at which this first neo chunk wins is that C over C plus C, and then is C over C plus A. And the probability at which this third neo chunk wins is the A over C plus A and the C over A plus C. And in order to make these 2 quantity equal, we'll have that A equals to C. That is, each chunk will be mapped to a neo, will be mapped to the same value as neo. So in this case, f of f is actually an identical function that maps every chunk to C. This case is quite trivial. So from here on, we may assume without generality that C equals to 0. So now we know that f maps neo to 0. Then we are going to establish this identity. That is, f maps k times the chunk to k times f of chunk. So we're going to consider this scenario, and we'll use an induction to prove this identity for each k. So here we are going to hook 2 identical chunks on this leaf, and the probability that the chunk 1 wins is x over A plus x. times the A over A plus KA. And the probability that which chunk 2 wings is actually A over A plus X times the A over 0 plus A. So in order to let these two quantity equal, we're going to establish this identity. And as for the final step, we're going to establish this final equation, that is F is indeed linear. So we're going to consider this scenario. We repetitively hooked these identical chunks on the lips and hoping that the probability at which these chunks wings are equal. So the probability at which A1 wins is actually X over X plus 2A and times the A over A plus B. And the probability at which A2 wins is actually 2A over A plus 2A over X plus 2A times A plus A times A over A plus A. So in order to let these two quantities equal, you can establish this identity. So here we establish the equivalence between the permutation invariance and the additivity. So a question naturally ensue would be, what form of an additive function can be? So here we give this answer, that is, any additive computation function must be of the form given by this formula, where there's some constraint on the coefficient here, that is C1 must be non-negative and the absolute value of C2 will be less than 1. And it's quite look like a plain linear function, yeah. So the proof set would be there, is depicted there. The gray region here depicted the feasible region of all chunks. That is, the intensity must be greater than the absolute value of mood. And we're going to concern those lines emanating from the origin with constant slope. So we'll define the GK here to be partial mapping that which maps X to f of X and Kx, where K is the slope of this line and it has an absolute value no greater than 1. And by a simple calculation, we're going to discover that GK is actually linear. And we're going to look at this equation. It is a quintessential Cauchy equation, and its solution can always be expressed as the linear combination of its value on the Hamel basis. But luckily, here we have an non-negative requirement, so we can write in affirmative that the solution of GK must be a linear one, where HK is a slope, a number depending only on K. So the edge maps -1 and 1 to a non-negative value. And in order to discover some property of H, we actually could represent H of Y as this linear combination, and we will find that it can always be represented by a linear combination of H of 1 and H of -1. So this indeed actually gives our final answer, that is, H of Y must be linear. Since the slope be linear and the GK is also linear, combine these two results together, we will get to the final conclusion that this additive function must be of this form. Yeah, and this is our first two parts. Let my partner introduce the sleeping expert problem. Yeah. Hello. Yeah.
Yes. Good morning. 我先共享一下屏幕。Good morning, everyone. I'm Lin Xiaozheng, and now I will talk about some applications of our additive CTM model and additive competition function. We have shown that our model can be applied to the snipping experts algorithm. First, I will introduce this problem, and in this problem, there are n snipping experts who can either make a prediction on any given example X or stay silent. When it makes a prediction, we say it fails on X, and when it stays silent, we say that it is a snip. And the expert is denoted by the notation HI, and the notation S denotes the all examples, and SI denotes the example that the S snipping expert makes a prediction on, and the notation L denotes the mistakes that an expert with a designed algorithm makes on an example set T. And there is a special case for snipping experts problem where experts actually never fall asleep. And in this case, the problem is just the familiar problem of combining expert advice. So the snipping experts problem can be seen as an expansion of combining expert advice. And the previous researches has established an algorithm which uses multiplicative weight update, such that its expected weight on each SI is not too much greater than the loss of the corresponding snipping expert HI, as shown in the equation 2. And in this equation, the expectation is over internal randomness of the algorithm, and epsilon is a parameter of the algorithm. And our goal is to perform the previous algorithm in CTM architecture. And how to perform it? We say that in the prediction making step of the previous algorithm, we need to randomly choose a snipping expert with this probability, and that is its weight divided by the summation of all weights. And the form of this probability is very similar to the probability that each chunk produced by CTM processor eventually reaches STM, as we have noticed as
We're not hearing anything.
Maybe there's a network interrupt from his side. Let me see if we can contact him.